I'd like to thank Magnus and Jens for this invitation. It's a pleasure to be here. And I'm going to share a slightly different perspective with you that's coming from an effort that I'm involved in trying to re-architect the internet. And in a certain sense, I have to disclose that I'm working on 2G rather than 5G that we heard a lot about. Internet is still in its 1G phase, and it may remain forever in that phase if things continue as it is. But it's an interesting opportunity now, with mobility becoming important, to re-examine what's going on. So again, for this group over here, I don't need to go into the details of this point. I'm just making the same point that others have done, which is to say that the growth of mobile data, it not only drives consideration of higher capacity wireless network, but at the same time, it should focus our attention on things like how to better and more efficiently integrate cellular architectures with IP in the short term, and that's been going on. And of course, in the long term, why don't we think about mobility as a primary use case or design requirement for the internet? So that's something that's just beginning to occur in the community. And before that, I just wanted to again give the background that we all know over here that we have seen a steady evolution from the cellular industry side of architectures which are more IP compatible. So if you look at going from left to right on this picture, we see that by the time we got to LTE, things are quite IP based. There's still a couple of gateways. There's an MME and a service gateway. But those architectures are what people consider to be IP compatible, but they are not completely IP based in the sense that the key mobility services are still provided by custom components in the mobile access networks, and internet is still viewed as a fat pipe that you can use to connect to the rest of the world. So with this type of evolution is where we are today with LTE, and there's now an opportunity to think a little beyond that. So I have a picture here, which is maybe a little bit too busy to show that there are two trends in the world, which here we are mostly talking about cellular industry trend, which is on the top side, and on the lower part is the internet industry trend. So again, the internet industry has gradually evolved some of the protocols. There are some big events like the release of BGP around 1990 or IPv6 just before 2000. Then there are other technologies that people are pushing today, but really not a whole lot of action in the IETF in terms of major big standards being done. If you look on the top, of course, this is a very familiar chart, and we have been evolving from 3GPP with ATM and so on to IP-based architectures, and eventually to flat IP-based LTE. I think a very interesting part of this picture is that at the same time, there's been the addition of the service layer, which is the key component of both architectures. And we see actually a lot of the innovation has moved from the core transport technology track to the services. So the pink boxes on top or bottom, web service, VoIP, SIP, CDN, OpenDNS that Google has launched, cloud services, all these are available to help the new generation of applications. But if you think that all applications are going to be mobile, there's already like, what, 60% of applications have moved to mobile platforms, then the top trajectory matters. And what I've shown over here is that with all this happening and taking stock of what we have today, there are a couple of disruptive technologies that are on the horizon for both the top and the bottom trajectories. So on the top path, we can see 5G is a sort of a disruption. It's something that has another 5 to 10 years before it happens. So maybe there's opportunity to rethink networking. There's also new technologies such as software-defined radios or open virtual base stations. The previous speaker mentioned that that's a very important trend with networking technology, that we will see the emergence of virtual networks and the ability to create services on top of them. On the bottom side, we also see a huge change in the fact that SDN got introduced last year. The whole networking industry, which was kind of slow for many years, has picked up speed, and they're introducing new customized solutions and protocols in a more programmable manner on top of IP. Typically, service level innovations are being done as we speak. And at the same time, in the more research community, which I represent, there's initiatives called ICN or FIA, which are the information-centric network or future internet architectures, which could be a disruptive change to this equilibrium that we have had with 1G and moving towards the 2G of networks. So what I am looking at is, let's take a step back and try to see what the future internet protocol, if we could ideally place something in the middle there, which is neither a cellular industry nor a internet industry, but something right in the middle, recognizing that these two industry tracks have fully merged. That hasn't happened yet. I think this room is evidence of that. If we go to an internet community meeting, see a completely different set of people with different issues on their mind. They say, oh, what is 5G? You guys are crazy, you know. So there's a very different mindset, but they're all going after the same customer, which is the smartphone, tablet customer running different kinds of mobile applications. So in that sense, the distinction seems unrealistic. Okay, so what do we think are some of the next steps towards cellular internet convergence? So in this chart, I've tried to show that we are at a pretty clean, if you look at the left-hand side, that's the LTE architecture with the MME and SGW that we're all familiar with. Can we evolve this towards a flat, completely flat architecture, which has no gateways at all, and uses distributed IP layer processing to do all the basic mobility, transport, and service management functions? This is, of course, not possible today because most of the routers don't support that, but can we build an entire edge network where you can just plug in a radio? And I think the emphasis of our community, this is a controversial point I'd like to make, is that our community has for years focused on radios and built networks on top of them. We should not continue to do that. Radios will evolve. There's a lot of innovation in the radio world. We need to decouple the two. Networks have to meet a set of functional goals. Radios have to provide wireless access. The two can be linked through a very simple interface, which is the standard IP, future IP interface as shown over here. So the idea is that both inter-domain and intra-domain protocols become mobility aware, and you simply plug in a radio. So whether it's Wi-Fi or some small cell, new technology, Bluetooth, whatever radio you have, you just simply plug that into a standard interface, and everything mobility services are provided by the network. So that's the vision. So now I would like to just walk through very quickly some of the requirements that we identified in trying to think about how to achieve this vision. So this, of course, is a very simple picture that shows the need for basic mobility. Device mobility is something that we all know how to handle, so I won't spend time on this. User moves from one access point or base station to another. You want to be able to maintain the connectivity and deliver data, continue to deliver data to this device. The more interesting thing comes up with the fact that you can have a lot of disconnections and bandwidth variation. As speeds increase, we are going to see increasing problems of some hotspots, but at the same time places where you have no useful coverage. So with that, what we saw, we have made a lot of measurements in the field, and we saw that, for example, with the 4G deployments that we have experimentally, we saw a lot of the right-hand picture shows some of the bitrate properties of a 4G network that we have running experimentally. And we often see that there are deep holes or disconnections. So we need to design a protocol which is not like TCP/IP that assumes continuous connectivity, and be able to do things which are much more efficient under disconnected environments or with high variation in the bandwidth, which also tends to mess up TCP/IP. So we need to rethink the entire protocol stack. There's another type of requirement which I think is fundamental, that of multicast as a basic network service. So historically, unicast has been the basic service, and we build multicast protocols on top of that. But if you look at wireless environments, we often have situations, machine to machine, or various other applications where multicasting is a very common type of requirement where a single packet that goes through the network should be able to exploit the broadcast medium, for example, or should be able to go to 10 cars on the highway instead of individually being addressed to all of them. This is again counter to how the IP works. So today IP is built on unicast, and then you have to set up separate connections for each of the cars that you're trying to address. We'd like to have a fine-grained packet multicast that allows you to say, send to this set of people, and it just automatically replicates and goes through the network as shown there, taking advantage of broadcast spectrum where available. So the other interesting requirement that, again, we are quite familiar with is that of multi-homing. So multi-homing is a very tricky thing. So actually, we know how to do it under certain 3GPP specs, but it can be very complicated, and IP, of course, doesn't support multi-homing. If I have two interfaces, by definition, there isn't even a proper driver for that. So in order to be able to do proper multi-homing, I need to have continuous connectivity to 2 or more networks, and I need to have policies such as best path or all paths and other things which the routing layer is actually in the best position to adjudicate. So I just want to make the case that also, when you look at these two networks, remember that the wireless access network number 2, which belongs to a certain office in a complex, and network number 3 belongs to AT&T mobile services. These are two different domains. So with IP interdomain architecture, it's very difficult to run this kind of protocol where you're going through two domains, and the routing layer can properly identify how to split the traffic and route it towards the two directions while doing the multicast implicit in this operation. So this is an interesting requirement. A related requirement, which is something that we all need to think about, is about the notion of multi-network access. So it has some similar properties, but multipath is something that would allow us to achieve the gigabit per second that we talk about. So in many situations, the radio may not be able to operate by itself at 1 gigabit, but parallelism has worked in the computer industry, and it will work here too, where having multiple paths into a mobile is a better way to increase its speed than to just have one path. And the reason is you get diversity of channel conditions, and you're able to go through multiple networks with different congestion and thereby create a more robust service. And of course, it's a business model issue. So we see today that I have a service with Verizon Wireless which locks me in, and I can only use that network. But if I had a multiple set of SIM cards which are authenticated for a couple of gigabytes of data a month, I could mix and match those services and achieve much better performance as I go through the world. So there's some very interesting things we can do with multi-network access. Remember also, this becomes an inter-domain routing problem. It's not the classic local area network. Let's figure out how to combine a set of signals. Okay, so another type of requirement which goes more towards services and content is that as a mobile moves around, very common requirement is the notion of accessing content efficiently. So in this picture, we show that a mobile might just want to be able to say, get content ID, or for the upload that we just discussed, you want to be able to say, send this content to a given user. And that's a very common primitive that we're going to see, where we're dealing with an entire file or a piece of content with a unique label. And then the network needs to be able to efficiently deliver that using possibly in-network caching, as hinted here in this picture. So this is another very interesting requirement that has some commonality with content, is the notion of context. So I think that if you look forward, a lot of the services in mobility involve the notion of context. If you do machine-to-machine communication, you want to address certain number of cars which are on a piece of highway, or you want to have taxis in a city or some area at a given time. So context has a number of attributes, and that's a whole another discussion about what constitutes a standardized context. But once you have that, we want to be able to run a network that can understand that context and then deliver messages based on that context descriptor. So we see this as a very important service requirement for mobility. Then I just mentioned here ad hoc and network mobility. This is a specialized requirement, but it would be nice to have the ability to create peer networks along the edge of the internet and be able to use standard inter-network protocols in IP to be able to continue to maintain connectivity between groups of cars, between sets of people. There's a classic Times Square scenario where there's 100,000 people or 1 million people gathered for Christmas celebration or New Year celebration. How do you maintain connectivity in that environment with a hierarchical network? So that's a hard problem. Again, a lot of solutions have been discussed in the academic community. We need to enable those by having networks which can operate in a peer-to-peer fashion as well. Then finally, I just mentioned here that spectrum being as important as it is, might be nice to have some management plane features that allow you to coordinate spectrum between networks. So when we talk about Wi-Fi doesn't work, it doesn't work because the Wi-Fi networks don't know how to communicate with each other. But if you have this stadium scenario that has been mentioned, two different operators can put hundreds of access points there and mutually destroy each other. So we can have a network service that allows you to coordinate and better understand each other's traffic and deployment patterns for any kind of small cell deployment across multiple technologies. So this would be nice to have. Okay, so I want to now spend a few minutes explaining our particular solution to this problem. We recognize this is a clean slate solution. It's not going to be adopted by everybody overnight. The idea is to build something and then extract key ideas from that, which will then go into standards and so on. So bear with me a little bit. I'm not trying to sell you a package which cannot be deployed on the internet today. But the basic idea is, if you go through my previous slides, to take these higher level requirements, take them together and try to map them into an architecture which looks something like what we've shown on the left-hand side. On the right-hand side here, where we say we have a network transport layer, which is sort of the core services, which will be the universal IP protocol of the future. And then on top of that, we have a new notion of having a well-defined set of network services, which then interface with your application providers or mobile clients, sensors, and so on. So the mobility-first architecture is aimed at meeting these requirements and coming up with a complete IP stack for services and control that will meet these and other anticipated requirements. So just a summary of the architecture that we have proposed. The top left-hand side is the key point that we now have migrated. In order to meet all these service objectives, there's a scientific problem here that IP addressing was designed at a time when a device is equal to a name or an object. But today we are seeing that the objects that we deal with, whether it's a multicast group, a set of cars, or even a device which has two interfaces, are more abstract objects. So a network attached object should have a name instead of an address. An address is a routable item which is a port on the network. So an address should specify the network port, whereas a name should specify the object which you're trying to connect to. And that object can be a compound object like a group of cars, or it can be all the devices a person owns, and so on. So there's a variety of different objects that we can create, which are then attached to the network. And then we'll have a binding between the name and the address that we'll see later. So the top there says that you have a human readable name for devices, for movies, for taxis, for context, and then these get mapped through a public key, globally unique identifier called a GUID. So really that's at the heart of our proposal, that everything is given a GUID. The GUID is a flat identifier. It doesn't have the properties of an IP address with hierarchies. It is completely flat, and it can securely identify any object that is connected to the internet. And we are now talking about hundreds of billions of objects to go after the scale that is expected due to mobility and machine to machine. Now, once you have that object identifier called a GUID, what we now have is a device will have a GUID, and it can now communicate with the network on multiple paths, because a GUID can be bound to multiple network addresses and then go through a network which has some features that we have defined. One key feature is storage-aware networks which allow for some storage to deal with disconnections or variations in channel quality. We also benefit in terms of caching and content caching. We have routers with integrated storage and computation, and we also have below, as you can see, ad hoc and peer-to-peer mode. So that's the overall landscape. I'm not going to go into every detail over here. Just let me walk through a couple of examples to properly to explain this and be able to understand how the whole architecture works. So again, just to show you the components of the solution, we have now split the architecture into a core transport service layer, which includes something called a hybrid GUID and network address-based global routing protocol, which takes into account names as well as network addresses. You have a storage-aware DTN routing layer, which allows you to deliver packets reliably even though you have disconnections. And then you have hop-by-hop transport, which gets rid of TCP and this 50-year-long principle of end-to-end connectivity in the internet being violated, but we think it's well motivated by various results that we have. On the top layer now, which is the services layer, we are creating a name-based service layer that allows you to construct services such as mobility, multicast, content, machine-to-machine. And we also have a more ambitious piece in this, which is an optional compute layer, which is a programmable plugin that allows you to expand services and extend towards some interesting new capabilities like transcoding, caching, and so on. So this is the overview. And the protocol stack that comes out for protocol engineers, the stack is very important. And we have here this so-called narrow waist of the protocol, which is the GUID service layer. So that now becomes the narrow waist instead of the IP address-based network routing layer. So the service layer is dominant, and below that I can run IP in a backward compatible way and get some fraction of the benefits of this architecture. In fact, we have already released a GUID service which is running right now. If somebody is interested, they can run it to find where their objects are and use that to run certain applications. We have a compute layer plugin option, which is the green box there. And below that, we have the more classical transport layer components, which are supported by a routing control protocol and so on. The interesting and totally new thing in our architecture is the GNRS, which stands for Global Name Resolution Service, and the network certification service that sits on top and assigns names to it. So the a little more detail on this is shown here, that when you have a name given, how do you get names? So different devices shown over here will go through naming services. These naming services, unlike ICANN, do not have to be unique or centralized. They can be decentralized, industry-specific structures which give out names. And the reason why they don't have to coordinate is because the total GUID space is very large. So each service can pick up GUIDs, and the probability of collision is very low. Below once you have this, there's a global name resolution service which binds network addresses dynamically to GUIDs, and that's how the whole system works. So I'm going to skip over some of these and now just explain how we could build a mobile network with mobility first. So in this architecture, you see the top picture is the traditional mobile network model. What we can now do is we can build a loosely coupled network of networks in which you now have mobility first running in all these different networks. These could be ISPs, which now begin to look like collectively they don't do anything special for mobility, but because they share the services of the network, they can act as a loosely coupled network of networks for wireless. So that's a philosophy that we have, and using this simple architecture, you can get this thing. So I just want to, I think I have 2-3 more minutes. I just want to give a couple of examples to show you how the protocol works. So the mobility service, basic mobility service is handled in this way. You get it, so somebody wants to send a message to John Smith 22's devices. Now this is an example of an abstract name. So I want to send to 2 devices. One is a smartphone, the other is the laptop. So I will go to a name certification service, get a GUID, And then the person who is sending to me, this is a service which I subscribe to, will get that GUID from the same name certification service. Think of this as DNS-like services which are available across the network. And then this guy will now put the GUID, which corresponds to those two devices, into the header, and then start sending the packet. What will happen at the first router here, there will be a lookup to the GNRS, which is a logically centralized but distributed service that allows you to find out that this GUID is mapped onto network 99 and network 32. So those two addresses are appended to that packet, and there's a service identifier saying what kind of service that it is, and then it goes out, and each router in a stateless hop-by-hop fashion examines this packet and forwards it. So in this case, once we have these NAs found, you can use a fast path routing procedure that doesn't go up to the service layer. It just cuts through at the network address level, reaches these two destinations. So I have sent a packet to all of John Smith 22's devices. So let me conclude by just showing you one or two results. So one important result we have is how to build this global name resolution service, because that is central to the architecture. We use peer-to-peer DHT technology to solve the problem, and every router here is doing a hash and updating, and I won't get into that detail here. If you're interested, please talk to me afterward. There's a lot of technical material coming out of this project. If you look at the website, you can find some of this. This again shows that we can get a 95th percentile latency of about 100 milliseconds using a K-hash technique, which is used to maintain a distributed table of GUIDs to network address bindings. And this is again showing that when you have an actual physical environment where people have mobility traces like this, you can look at the CDFs of the number of updates and so on, and you can get pretty good performance with that. So just to conclude here, I want to say that a router in Mobility First now is a new kind of router that we have implemented so far on 2 or 3 technologies. We have talked about SDN today. We have a SDN implementation of Mobility First. We also have a software implementation. Router has 2 planes. The lower part is a more traditional network address-based forwarding. The upper is the virtual GUID to address mapping table. Each router has access to both, and it can do a variety of services by building on top of that functionality. So let me conclude here, and again, I would just point you to a couple of, you could look at the slides, and I just want to point you to the website on which the top pointer is for the website, which has a lot of technical information about this project. And please contact me if you have any questions.
So let's have a few questions. So start with Celine.
Yes, hi Ray. Very interesting, although I have to say that it's not really my field, so I'm lost for the most part of it. But I remember in the middle of the 90s, the first time I was representing AT&T meeting with IETF Architecture Board, and the talk I gave was when wireless meets IP. And I kind of highlighted the 3 elements: mobility, security, and QoS, as the 3 key things that when wireless meets IP needs to get resolved. It seems that a lot of effort has been going on in these 3 dimensions. However, more work needs to be done. But specifically for mobility, that seems to be the focus of your work here. I remember in the late 90s with Charlie Perkins, we kind of had all kinds of variation of this mobile IP. Eventually we gave up because our mobility management for the most part is a layer 2 function, it's not a layer 3. But while I'm kind of lost in your architecture, but I noticed you mentioned that this GOID service as the new waste, which seems to be 1 layer even above the IP layer. So I'm just wondering how there seems to be, I'm a little bit lost in the logic of how you can handle the mobility we really need in the wireless world at even higher layer.
Yeah, so the reason to move up 1 layer is that mobility has to do with objects that migrate across the network. So if you can move from addresses to names, the reason why mobility is hard to do today is because we equate, IP equates an address with a name. So you have to have two addresses for mobile IP, one which is your home address, the other which is your current address. You have to do IP in IP kinds of solutions. Whereas once you have a unique name, you say send to this person. So if you say send to Ray, that is a unique name, and that person can be found wherever they are. Of course, the fundamental requirement is that you need a logically centralized global name resolution service that says that this person is currently located at the following IP addresses. So that's why we move it up. So if you're doing multi-homing and I'm connected to two networks, one Wi-Fi, one cellular, that global name resolution service maintains the dynamic binding between that name and the set of addresses. So that's why mobility is a higher level logical construct than routing. Trying to push it into routing layer was the mistake in the first place. And you talked about IETF, so again, a lot of efforts were given in IETF to all these things, but nothing happened. And the reason is that incrementally these problems cannot be solved without a proper architectural framework, which never existed. IP was invented 50 years ago, and none of these were thought about at the time.
So, okay. And then Lowry.
Thank you very much, Professor. You do provide us a very, maybe we can say it's a clean slate mobile internet system. But yes, I think first is the mobility issue. I think if the mobility over layer 3, that's no problem for some kind of service. But for the only for central system, we provide so-called seamless handover. So that's why engineering says that we need layer 2 or MAC layer handover. So we need a seamless handover. For the if on the layer 3, I think there is some difficulty to reach the seamless.
Right. So yeah. So let me.
It's the first question.
Okay.
Another one is that you use the global name resolution service and use the new ID. But I want to ask what's the difference between this new ID and the IMSI? I mean the USIM card ID of the mobile terminal. So what's the difference of these two? What's the different function? And sorry, I have one more question.
Perhaps we should start with two here, so we get questions here, please.
And the next one is the operator's core network. In your new structure, you throw out the charging system, the 3A system, and also the MME or some mobility control system. So I think it's not a backward compatibility system. I mean, all we can difficult to see where is the current operator's core, where it is in this whole system.
Agreed. So,
okay.
So I think all are good points. Let me answer very quickly. So the layer 2 support for mobility is no problem. When you have layer 2 support, you can still utilize that. You move up to layer 3. Here layer 3 actually means the GUID service layer, not the routing layer. You move up when you need to. So when you have inter-domain mobility between Wi-Fi access point and cellular, or you have dual homing across those two networks, you use layer 3. But internal to a network, as you move around, you could use layer 2. So that's fine. Okay, and so I think your other question was about compatibility. So how do this is not a compatible project so far. This is a clean slate design. Our goal is to complete and demonstrate good results. If we get, we talked about 10x, okay, we already get 3x, 5x gains relative to TCP in different use scenarios. And that will depend on, are we talking about or vehicular mobility or human mobility, machine, each case is different, right? But you can get large gains, and our purpose is to show this, and then some parts of the idea can migrate into different standards. We are not talking about an overnight change, but in 2022, maybe there will be a new way to think about. And you saw some of the speakers at this meeting also talking about virtual networks and services, and that becomes far more important than the pipes. But network operators will become obsolete if they don't upgrade the quality of the network, which must be service-oriented instead of routing-oriented. So did you have you had a third question? Okay, so IMSI is an example of something like a MAC address. Okay, a MAC address could be similar to a GUID, but it's not, because MAC address defines a device. A GUID is an abstract end quantity which can have multiple devices. It can be a place. It can have many. It is more abstract. It doesn't require a piece of hardware. So up to now, our industry has been talking about device identification and device mobility. This is more abstract service mobility that we're looking at. So GUID is a more general, but GUID is also a public key using cryptography to maintain privacy and security on the key.
So Laura gets the last question before coffee here.
Thank you. So thanks for a very interesting presentation. I think it highlights, again, the kind of how little we know about the future, so also the assumptions on the networking side could change by the time we are doing a new air interface. I agree that we have been also participating in this ICN research as Ericsson, for example, and some others. So and I think, in my view, being able to decouple the host and object names would be a good idea. So far, I haven't really seen a good migration, let's say, plan how to do that. So if you could come up with that, that would be great. I agree that the kind of basic mobility with some of the speakers here on the seamless mobility that we need to have underneath, but that's a different layer. And this just shows how there are different ways of doing the core network or the kind of services on the mobility, security, authentication, etc. As I mentioned, and we also did when 4G was being developed, we had a proposal on proxy mobile IP, which was kind of, well, industry decided let's stick with GTP, and there is not a huge difference on the performance. So also I think that it would be really good to see more. We can't do it here, but see more what actually would be the improvements that can be gotten with this clean state approach, because that was a little bit still left that there are a lot of change, but what are the main improvements beyond the kind of separation of host and device?
Right. No, thank you for your comments. So actually, I just want to, speaking about performance, we actually have a lot of results already being collected through a large-scale deployment. So what I talked about is not theoretical. We have a large deployment of mobility first across many sites internationally. We also have two, the yellow ones are the wireless access sites. So in these we are doing testing of sort of short-range wireless performance as well as global internet performance. We have a name resolution service deployed. We have a couple of papers that describe our experience with that. So the performance is, as far as we see up to now, is pretty good, but we are still dealing with a clean slate solution. If we look at overlay solutions or being able to migrate, there are many good things happening now that make it easier than before. With SDN technology, we found that many of the networks we're dealing with have SDN routers, so we're able to do some things. But the full evaluation will take 3 more years. The phase of that project is just starting now.
Yeah, so final thank you to Ray.